Good morning, everybody. It's a great pleasure to see all of you here back. I hope you had a good rest last night, because now we have a truly exciting session where the ingredients come together to be treated with technology and to become a product. It ultimately needs to be accepted by consumers, but needs also to carry lots of nutritional value. And the question is, how can technology actually enhance or preserve nutritional value that we bring into the ingredients by various measures that we have discussed already yesterday. And we have also a geographical journey ahead of us in terms of the origins of our speakers. We first go a little bit north with Professor Remko Boom, and then we go deep south with John Taylor coming from South Africa, and on our way back we have a stopover in Ghana where Faustina has her affiliation at KNUST, before we finally go back to Switzerland to Zurich with Peter Staar from IBM Research. I will introduce them one by one as they are being called for the presentation. So now it's my pleasure to ask Remko Boom to join me here on stage. Remko Boom is a professor at Wageningen University Research for food process engineering. Remko has done his master and PhD at Twente University, and then shortly after joined Unilever to gain some experience in practice, so he knows what it means actually in an industrial environment to process food. Yeah. And then he was appointed already at the age of 33, I calculated, a full professor in Wageningen, which is pretty early, and congrats to that. And since then he's building up his team, a huge team with today approximately 60 PhD students. Yeah. So that's a pretty huge cohort, and you can imagine the number of publications and the knowledge which comes out of that group. That is truly impressive. So we are very pleased to have you here, Remko. And your talk is about how to preserve and leverage actually nutritional value with new technologies, right? So I hand over to you, please.
Well, thank you very much for this very kind introduction. Actually, thank you for inviting me to this symposium with this very wide scope, which is really inspiring, I think. And I hope that you will find the perspectives of a simple food process engineer also useful today. And especially, I would like to talk about what we can do actually in processing to combine really better sustainability, resource use efficiency, and also contributing to nutritional value, you might say, simply by preserving the natural goodness in ingredients as well. Well, of course, we all work very hard nowadays to switch from animal-based protein foods, animal-based foods towards plant-based foods. And the reason is obvious. We can actually save a lot, at least in terms of the growth, the cultivation of the raw material. It's really clear. In this case, the indicator is the equivalent CO2 emissions, but you can see it is really better compared to meat. However, if you take the total chain into account, the whole thing is a bit more complex. There you see that in fact processing, for example, in this case proteins, and getting proteins out of the raw materials is not so easy and takes a lot of effort. And that means that we have to be careful that we don't fool ourselves if we switch towards plant-based protein foods, that we in fact are not so much better in terms of sustainability. Well, the reason is that if we want to isolate the protein out of a plant crop, we basically, usually we dissolve the protein at a higher pH, pH 9 for example, and then we precipitate the protein again at a low pH, pH 4.5 for example. And the problem is that not all the proteins will actually dissolve in the water, and not all the proteins that have been dissolved will then precipitate. So it actually means that we do lose quite a considerable amount of material in the various side streams. And then since we use water as a process aid, it also means we have to remove it. And of course, that also requires a lot of energy in terms of drying. So there are some disadvantages, which are, it's a very effective process, but it's not so efficient. Well, in the last couple of years, we have looked a lot at a very radically different way of working, which is in dry processing. We basically just start with milling. Of course, you have to make things available. And then we simply use a mechanical technique like air classification, which is simply blowing at the flour. And then, well, the smaller particles which contain the protein will be blown farther away than the heavier starch granules. And this actually gives you a nice separation. It does not give you pure ingredients, but it actually gives you enriched ingredients. You can improve that by adding electrostatic separation, which is basically rubbing the particles over a surface. They will get an electrostatic charge, depending on their material. And if you then subject them to a transversal electrostatic field, then actually you will see that one type of particle can be collected on one electrode and the other on obviously the other electrode. And that gives you actually an even better separation. Still, you have enrichment, but no pure protein. But the graphs actually show you that the amount of resources that you need is really a lot less. Obviously, with dry processing, you don't need water, so that really helps. You don't need energy to remove the water. And the nice thing is that all the streams remain in the solid phase, which means you can easily store them, trade them, transport them, and also use for other purposes. So that's actually quite useful in terms of sustainability. Of course, there are also some intermediate forms. For example, we look a lot towards hybrid separation, where you combine dry separation with a very mild aqueous treatment. You basically suspend and sediment it. That already gives you a lot better purity of the proteins. And there are some other hybrid processes as well. And if you then compare what you can actually do with these processes, we see that, for example, if you look at the dry processes, which are the lower ones, you see that the effort that we need to do for processing is a lot less, obviously because we omit water. But you also see that the green part, the cultivation part, gets less. And that's because we actually have less losses. So for 1 kilogram of protein, we can actually use less of the crops. And that's of course important because it saves over the whole chain. So in terms of dry separation, this is really better. If you want to go towards higher purities, you can have these hybrid processes. And you see that with P, the lower one, that can actually also be quite nice. And actually combine it with higher purity. But for example, with looping, you see that it's a bit more difficult. So this shows that per crop, we actually have to see what the best possible process is. Well, in general, we see that if we look at very many types of processes applied for very many types of crops, we see that the amount of effort that we need to put in the process to get a protein purity really increases very rapidly. The vertical axis is a logarithmic axis here, and you see that if we go from 20 to 80% of protein purity, we have to put in 100-fold times more effort, in this case expressed as exergy loss. And then if you go above 80%, you see it's even stronger than an exponential increase. So it shows that, yes, going towards higher purity has quite a big cost. And that's something to realize. Interestingly, it might just be that we don't need such a high purity because usually end products are not pure, they're usually also mixtures. So maybe if we can use them as a sort of precursor of products, we could actually capture the reduction in the use of resources. Well, one example is dry separated starch from pea. And here we found that this typical fraction is about 68% of starch, so still about 32% of fiber. But the amount of thickening that we could reach with this fraction is actually quite similar to what you can reach with 100% starch. And that's of course interesting. First of all, we use more of the raw material. Secondly, we actually have more fiber in our products, and of course we like that. And you see that, for example, other properties like the synergesis actually compares rather favorably compared to the pure components. So we might not need the high purity if we actually look for specific functionality. Of course, the ingredient which is most interesting is protein. And also here we see interesting behavior. We basically see different properties than we would expect from a pure protein. For example, if you take these dry separated proteins, you can simply disperse them in water and still have quite a fluid liquid at up to 40-50% of solids or so. If you compare that to a commercial protein isolate, you would see that that would solidify at much lower concentrations already. We can also make very nice emulsions with these components, and surprisingly, if you, for example, bring the emulsion towards the isoelectric point of the protein, the emulsion is still stable. It's of course interesting because usually if you do that with a pure protein, the emulsion would not be stable anymore and it would cream up. Similarly, if you freeze it and thaw it, also the emulsion remains stable. That is also in contrast to a commercial protein isolate. Well, interestingly, in the classical dissolution precipitation process, I said we lose part of the proteins. And some of the proteins that we lose are the albumins. The globulins, in this case P, are easily precipitated at their isoelectric point, but the albumins are much more water soluble, and they remain in solution even at those low pHs. So we typically lose them. Well, if we actually take efforts to recover them, we find that they have quite interesting properties. For example, if we have these albumins, they appear to be very, very good foamers, actually quite comparable to whey protein isolate. They give a very nice interface. They give excellent overrun, small bubble size, and also a very nice half-life of the foam. On the other hand, the globulins are excellent emulsifiers, and well, also they give good properties. If you mix them, they're slightly worse. But the nice thing is you can actually tailor the type of fractions that you can make towards the specific application, and therefore also tailor the function of those proteins. Also, if you recover the albumins, we can make much better gels. And pea protein is not known for its great gelling properties, but apparently if you actually can recover the albumins with it, you can make much better gels. And that's important, for example, in the preparation of meat analogues, where the gelation is one of the properties that we really need. Well, one of the obvious problems with mild processing, like for example dry processing, is that we might retain the anti-nutritional factors as well. Since we don't do a lot, we don't eat, for example, and therefore a lot of these ANFs may be still there. Well, we have to remember that at the end, if we actually use the ingredients and then have the end product, in many cases we do heat the products, and that might of course inactivate some of the anti-nutritional factors. Obviously not all. What we also can do is to have, once more, you might say, precision mechanical fractionation. For example, yesterday we discussed quinoa and the role of saponins. Well, these saponins are actually located on the outside of the quinoa shell. So if you mechanically abrade the outer surface of the quinoa kernel, you will actually lose the saponin content as well, pretty fast. And well, you can also, for example, use solid state fermentation, and that can actually quantitatively remove some of the anti-nutritional factors. Well, we've put a lot of work in developing an in vitro dynamic gastrointestinal simulator, and there we find that the bioavailability of proteins can actually be enhanced by mild processing, but if we process too much, then we actually see that the bioavailability goes down. And I think that with many of our processes now, we're actually over the optimum, so also there it might be beneficial to see what we can do. Well, we talked a lot about proteins. Oils are also interesting. You know that oils usually are extracted by pressing and hexane extraction, for example, but you don't need to do that. You can also do it with water. You simply take, for example, sunflower seed, you mill them, you expose them to water and remove the solids, and you'll be left with an emulsion which still contains the oil in the form of the original vesicles which were present in the seed. And the oil in the seed was quite stable, and therefore also here the oil is still quite stable because you still have the phospholipids and the oleosins and chaleosins, the proteins which protect the oil. And David Gray from Nottingham University actually showed that if you look at the oxidation of these oil bodies compared to human-made emulsions, which are stabilized by tocopherol, you see quite a difference in the stability. So if we retain this natural goodness of these ingredients, we might actually also have a better functionality of these ingredients. So I think in total, we might actually combine a number of things if we rethink how to treat our ingredients, because we might make a significant step in sustainability. We might even combine that with enhanced nutritional value. The consumer might actually like it because, for example, we wouldn't need any tocopherol anymore to stabilize an emulsion, and there might be some other examples of that as well. And if you think about processing less and at the same time also using more of the crop, inherently the cost should go actually lower than with our conventional processing. So in principle, I think this is an opportunity to grasp. Of course, there's also a disadvantage, and that is that these enriched fractions, in fact, can behave quite complex. They are very complex, so they also give complex functionality. It's difficult to understand their complete behavior, and therefore we decided to actually approach this with data-driven models. In principle, these enriched ingredients give us sufficient formulation space to actually make most of the products that we can make now. We don't need pure oil, for example, or pure proteins, because our products generally don't contain pure oil or pure proteins. But then, of course, if we can make the compositions, we also want to have the right functionality of these ingredients. So with that, we try to set up these data-driven models. So we basically map the functionality that we can reach with different types of ingredients. And then if you know that, of course, you can revert that and see what formulation space you would have to achieve the functionalities that you want. Well, you can do that with the typical isolates, which are the red components. That would be the traditional way of formulate a product. But then if you start to replace those with the more enriched fractions, you can actually see you can reach the same functionality, but with a significantly lower global warming potential or any other objective that you set. And that's important because we then can preserve the goodness of the product, but actually get a much better sustainability by preserving the goodness of these ingredients. So I think to conclude, that's a nice fit, I think, with the timing. To conclude, I think we should remember that the food is not just a set of molecules, and the same is true for an ingredient. Also, an ingredient is not a set of components. It actually has a structure, and if we preserve that structure, we can actually make use of that structure. So if we do not avoid the complexity but embrace it, I think we can actually go a long way to also contribute to better sustainability and better nutritional value in our foods. And as Christoph mentioned already, well, it's my privilege to talk about this today, but of course, please realize that there's a lot of people working on this. I just have the privilege to talk with it. So these people did the work. Thank you.
So good morning, everyone. Ah, that's good to hear. So firstly then, a huge thank you to Isabel and Petra from the Nestlé R&D team for organizing this absolutely fabulous meeting. It really is a pleasure to be in such august company. Thank you. Okay, so I've been given a very long title, Role of Food Processing in Leveraging Local Food Plants and Preserving Nutritional Quality and Security, with a focus on, and it was local food plants. I've added African. I make no apologies, because yesterday I think we saw that the real need actually for preserving and enhancing nutritional quality is in Africa. It's unfortunately or otherwise in sub-Saharan Africa is the most food insecure part of the world, with a dramatically increasing population. Okay, so this was covered yesterday, looking specifically at micronutrients, the focus on vitamin A, iron and zinc deficiency. I'm not going to belabor the point, but there's some frightening statistics. Okay, so I think most of us are aware of the strategies that exist currently to address micronutrient shortfalls. And so there's a non-food intervention, supplementation, typically given to infants, and then 3 different food-based interventions. Conventional fortification, obviously adding vitamins and minerals, in their chemical form, dare one use that word, to food products. Dietary diversification, what people have been doing for centuries, is eating not just grain staples, but also then a wide range of fruits and vegetables in a plant-based diet. And then more recently, biofortification, where those food staples, the content of the micronutrients are enhanced by various different technologies. What I'd like to do is to introduce you to a new technology, well, not new technology, a new concept, food-to-food fortification. And so we have a long definition for this with some rather important concepts built into it. So it's the addition of micronutrient-dense foods, and then there's to a recipe, for example, at the household level, to a food formulation at a food industry level, or the replacement of micronutrient-poor or anti-nutrient-rich ingredients to substantially increase the amount, another key concept of bioavailable micronutrients. We heard a lot about yesterday the issue of importance of bioavailability. And obviously with an objective to improve the micronutrient status of populations where the intake of bioavailable micronutrients is inadequate. And this is food-to-food fortification must be seen as a complementary strategy. So we've got a food pyramid, as it were, with food-to-food fortification sitting between conventional fortification, biofortification, and dietary diversification. And so if one then looks in the African context, then the opportunity lies in micronutrient-rich plant foods. And so we divide them into the grains, the vegetables, the green leafy vegetables, and the fruits. Then we see, and one can always argue about the numbers, because there's varietal issues, there's cultivation, soil issues, and also the way their units are expressed. These are expressed as is basis. They perhaps should be better if they were expressed in terms of people's intake within a food. But some are particularly rich. If we take the example of protein, Remko was discussing protein, then cowpeas being a pulse, far higher than in a cereal. Some are rich in provitamin A. For example, carrots, orange-fleshed sweet potatoes have been mentioned, moringa leaves, a green leafy vegetable, GLV. Some are rich in iron, for example, pearl millet and cowpeas. Others are rich in, or relatively rich in zinc. I think zinc is probably the one where overall the concentrations of the micronutrients are the lowest. So if you take then the staple food in much of Africa, which is a porridge or a pap, in this case it's pearl millet from the Sahel region in West Africa, if food-to-food fortified, then one can see that there's a role for various different additions. For example, moringa as a source of iron, carrots as a source of provitamin A, mango also as a source of provitamin A. But the key issue that we need to mention is that of bioavailability. And so some of these, what we could call food-to-food fortificants, these plant foods, are also high in enhancers of bioavailability. For example, baobab fruit is a very rich source of citric acid and ascorbic acid. Mango, a good source of beta-carotene and of organic acids. And likewise with carrot, a particularly good source of beta-carotene. So it's not just the content, it's also the amount of enhancers that are present too. And if we look now at perhaps a rather complicated schematic, which I have my postdoc, Ola Yumika Adetola, to thank for, that what one can see that on my left-hand side, we've got within the lumen of the small intestine, what then happens at the intestinal brush border membrane, within the enterocyte cells, and into the bloodstream. And the issue of then bioavailability is to get these micronutrients firstly into the bloodstream. And as we heard yesterday, that plant foods then are high in inhibitors of bioavailability, inhibitors of absorption. Polyphenols, for example, bind to iron. Phytate binds to the divalent minerals. The enhancers counteract those effects. So most notably, for example, ascorbic acid keeps the iron in the reduced Fe2 plus form. But also then ascorbic acid has multiple actions. It forms soluble complexes with particularly iron and possibly zinc as well. And similar then effects are believed to take place with citric acid and also with beta-carotene as well. So in other words, that one's actually having a battle, as it were, between the inhibitors and the of micronutrient absorption, and the enhancers, one hopes, is then working in the opposite direction. So what is the evidence that food-to-food fortification works? And unfortunately, the reality is there's far too little research being done to say categorically one way or the other. If we take the case of the green leafy vegetables, despite the fact that they have a high iron content, that iron seems to be very poorly available. And that's because in these green leafy vegetables, you have high levels of phytate, high levels of phenolics, but also high levels of calcium too, which form insoluble complexes. With zinc, it seems to be perhaps a different story. With fruits, despite the fact that they have low levels of minerals, the fact that they contain organic acids, ascorbic acid and citric acid, and in some cases beta-carotene, the evidence seems to be that they actually then promote mineral bioavailability. And so what we're going to start looking at then is some research examples. This would be really in terms of a recipe. So what people would do, conventional maize porridge, food-to-food fortified, then with baobab fruit powder. And as you can then see that there's some improvement in bioaccessible iron. This is measured by their dialyzability assay. One could argue just how much the numbers in such rather crude in vitro systems mean, but it is in the right direction. If one looks then, there was yesterday discussion about the bioavailability of iron fortificants. So in this case, we've added ferrous sulfate, the cheapest of the iron fortificants, and then what we observed was both an increase of iron and percentage iron bioaccessibility and of zinc bioaccessibility. Okay, so now we're going to then look at that last aspect in a way. So we said it's about adding to a recipe, it's about adding to a formulation, it's about replacing a component which was poor in micronutrients. And perhaps the most obvious one is that, curiously, most human beings eat refined cereals. And on the face of it, it's a pretty stupid thing to do. For many reasons. One can see in the green that if one eats whole grain cereals, not only is the protein of higher quality, has essential fatty acids, it's got tocopherols in, it's got a B vitamin and complexes, it's got minerals, it's much higher in dietary fiber, and it's got bioactives. All those are lost particularly in Africa, Africa is suffering the fallout of the war in Ukraine with a vengeance. That the prices of staples have increased dramatically because, unfortunately, something like 40% of our maize supply has to be imported. If people change from refined grains to whole grains, there's 25% more food per kilogram or per ton of grain. And that's a remarkable. Oh, that's so obvious, isn't it? But obviously it's not quite as simple. And I was speaking yesterday with Isabel, and she was talking about the problems in Africa that Nestlé has in actually obtaining grain of the right quality. The reality, there's common sense, unfortunately, in refining, because you remove sand, you remove other contaminants, you remove mycotoxins. 5 minutes, we're still racing now. Good. Okay, now we're talking more processing. This is a mini commercial extrusion cooker. So it gelatinizes the instantizes. Why the need? People lifestyle changes. With a huge increase in the mega cities in Africa. Women commuting 2 and 3 hours a day to work. No time in the evening to prepare. Instant, just add hot water. And this is a chain of adding nutritional and convenience to foods. Starting with milling, fortifying, adding protein, extrusion cooking, and then food-to-food fortification. Okay, some evidence that extrusion cooking actually then will improve iron bioavailability. And why we think so? Because of the destruction of both phytate and of the polyphenols. Okay, we're going to last look then at a case study. And this is a small enterprise in the Sahel region. And these are the beneficiaries of what small enterprises can do producing that kind of product. So the company last year produced 200 tons of food-to-food fortified cereal flour. And the beneficiaries were, it's a cooperative, the women grain processors, farmers, the women retailers, and then the end users, and the extra income, not just the direct nutritional benefits, but the extra income that they gained through, which supported their educating their children, and then supported the purchase of more nutritious food products. And we call this entrepreneur-led food fortification, and there's a value chain. And just the final point that I think I need to make is that conventional fortification and biofortification, they have their place, but they're imposed. They're what you might call top-down. They're done by the men and women in white coats, or the worst of the species are those like myself, those men who have 1 minute left, who wear the dark jackets. This is within a community. It keeps money within the community, and it can respond very quickly, this system, to the local needs. Okay, just to say then, thank you very much indeed for being invited. Also wish to thank all the clever people who've been involved in this now 8-year project, USAID project, which is called the Food Processing Innovation Lab, which is led by Bruce Hammaker. Also Mario Ferruzzi, who played a role in that I was here, and also my students. Thank you very much indeed. I'd like to talk for a lot longer, but I can't.
So, very good. Let me quickly get started. So I want to put a little, since this is going to be a bit of a different talk as all of the other ones, I want to just put it a little bit into context. I'm very deep in AI now. I did that change around 2014 when I jumped from high-performance computing to machine learning. But as a student myself, I was already struggling a lot with just understanding like what the latest research was, because lots gets published. And so I started explicitly with that goal in mind to start building technologies that can deal with that, integrate data and all of this kind of stuff. And in the meantime, also, in the last decade, AI has been growing massively, okay? So now then the question is, okay, how can we use AI in food safety, but also more generically in any type of discovery-led and science-led efforts? And so that's actually what my team is busy with. And first and foremost, like what we're not trying to do, especially in my group, is we're not trying to do AI systems that try to just answer questions or arbitrary type of questions. And just to give you an idea, there are different types of questions. There's like really super fact-based questions, such as like, okay, what's the chemical structure of fructose or something like that? Okay, that's pretty clear, everybody knows. But then there is also, and that much more interesting question, which is like, okay, what's your best diet? What's the most nutritious diet? Stuff like this, which there is a lot more controversy, there depends, and then all of these type of things. And so we are really focusing on that part. And, you know, when I was researching this talk and trying to see what we want to do, and also with discussions with like Richard that we had in the past year, there is a very interesting symmetry, and as a physicist, I like symmetries. On the one hand, what I've read here or heard a lot is about like how do you get from the farm or from the plant all the way the nutritious stuff to the customer, right? What we are trying to do in our team is exactly the same thing, but we try to get good, high quality data from many different sources to your screen, okay? And then it is up to you to actually make that decision and understanding what you're actually, or what the best course of action is. And I think this is the way we are approaching this problem. And where AI actually fits in is exactly in the point of actually leveraging all of the new technologies such that you can get this data out. Because the data is scattered all across the board. It's scattered in databases, it's scattered in documents, it's scattered in tables, it's scattered in figures, and so on and so forth. And so how do you actually extract that and make that available to researchers that then can make new data sets? Very simple example. You have a lot of different types of tables. Can you extract it from all of the different documents, stitch it together, and make a new data set that is much bigger, right? That's a simple example in our world. It can go beyond that, we're actually getting the data out from the figures and the text and so on. And so now just to bring it back, I mean, if you think about it, again, I didn't come up with it, I read a bunch of papers to try to understand where this thing is going, but at the end of the day, you can go all the way from production to suppliers, you go either in different types of geographies, across time, and essentially around this whole chain, there is many different steps that are being taken that produce documents, that produce data across the board, and actually how can we integrate that all together in one place so that you have a complete overview. And researchers can essentially start accessing it across the board. Of course, again, there is the public data that is probably going to be from academia, and then there is all of the whole stuff that is more from the proprietary part. And our technology is built in such a way that all of our public academic literature can go exactly through the same pipeline as that your proprietary data can go, such that you can actually also complement data that is data across the board. So what we are essentially doing is, and now that's kind of the idea, but then the question is how do you actually implement it? So there is a big part, so if you really want to think about like where all of the knowledge and data comes from, we are mostly focusing on documents, right? So there is, of course, the component with like videos and YouTube and whatever else. That's fine, but I think in real science, most of it goes through documents, and so this is what we are focusing on. And so essentially, we have a big component that is talking about, or that is actually working on fully automating. This is where a big part of the AI goes. You will not even know it, but this is where a lot of research goes. Very, very, very accurate extraction of the data and normalization, such that like if you find tables, you find properties, you find the units, do you normalize the units such that you can compare and so on and so forth. So there is that part that is extremely important. And then there is the other part that is, okay, once I have actually the data, I have augmented these, I have augmented actually the data from these documents. How do I bring it together? How do I link it together such that I can support contradicting statements? I don't call them facts because facts have people, connotate that with being true. you will find in many different documents statements that might be contradicting, and for a good reason, because there are conditions that are kind of silently not said. And so that's why on the one hand, we build a lot of technologies to extract the data from the documents, and then we have other technologies that then bring that in what we call knowledge graphs. And knowledge graphs are essentially, well, they're graphs, they're mathematical structures, there's nodes and edges, that's all it is. But the question then is, what do you actually put there? And we have done that now for material science, we have done that for business intelligence, and we're looking forward to also expand that in different technical fields. Actually, we also did it in oil and gas. And the nice thing is knowledge graphs, they have a very flexible way of thinking. You can put anything in a node, you can put any type of edges, and then the question is, which edges do you define? Which types of nodes do you define? How do you link them together in order to actually solve your problem? Okay? And there is not one fits all. We built a whole platform such that you can very quickly generate those knowledge graphs. Okay, so then basically, bringing it back together, really, now what is all of the research, all of the AI one needs to actually do that? Well, on the one hand, you have structured databases, you need to ingest that. You have unstructured data, typically coming from our documents. We define the schemas in such a way that we can interlink, because every database has a different structure. All documents have also different types of structure. So we have a common schema representation so that you can mix and match from your patents to your invoices. And then you have all kinds of different topics that you will need to address. One a bit more than the other, but it's a lot of different AI that goes in. Again, if you look at a lot of this stuff, all of the AI here is really meant to help you get the data out, not to get you the final answer for these rather complex questions. It's just something that is extremely important to do that. So you can really think about it like commodity types of things, not predicting like, okay, this is now the solution, that's the end of it. So now what is the challenge actually with documents? Well, if you have a PDF, and we're not even talking about like scanned documents, let's just take the simplest case, which is programmatic. Not that we're not doing scan, but the interesting thing is that if you open a PDF, and you might not know that, it's really like a printing language. So it just tells you this character goes there, or this line goes there. And if you're lucky, you get like the sentence, and if you're unlucky, it goes character by character. And if you're even more unlucky, then it is like you have a character, you have 3 characters, a character. If you have bold, they basically take the same characters and they shift it a little bit. So it's a complete mess. So saying that you can extract text from a PDF document, you can forget about it only if you're lucky. And so if you just dump the text, you get this nice sausage of a string, which all the information is lost. So that's why what we are actually doing is this part, right? So we have a document, and what we're trying to do is to put a lot of structure in there so that you can actually get the structure out. Now, why are we putting so much effort in PDF? It's because it is, by the fact, that the common way of how to communicate with each other. Everything goes through PDF, so we wanted to take, the most common format, and then if we can do that, we can do everything. We can ingest PhD theses, we can ingest scientific articles, we can ingest basically everything. And there's basically two big algorithms. I'll go into that a little bit. One is layout, so you need to group certain things. That is a big part. And then there is table structure, which is by far not trivial. Again, it looks trivial. It is surprisingly hard, and I can always find like one table that doesn't fit the mind. But I'll show you where that AI goes in. So one thing we are very proud of in our group is that we put a lot of effort in publishing and making things available. I'll show that a bit later too. So that on the one hand, we want to have an open hand, and like we're very collaborative with academia. So if you're struggling with this thing or you're interested, by all means, reach out. We are more than happy to work together. I also showed a few things that we are actually making publicly available so that you can get started. But also we publish at the top conferences. We put all of our papers on the archive, so everything is fully disclosable, and you can look it up. I just want to do 2 different AI algorithms that are in the bag that you can use. I'll show that later, but that just gives you a bit of the idea of the complexity of the problem. So we did one thing at layout segmentation. So the layout segmentation is I give you a page, like can you find the groups of things that are clustered together? Looks extremely simple, right? I mean, how hard can it be? It is hard. I show you that. So basically, there were a bunch of data sets that are out there, mostly on scientific docs, and there it is easier. I would say easier, I don't say easy. Then we started working on all kinds of things, from annual reports to magazines and all of these kind of things, and patents. And first of all, it is not clear sometimes how you should annotate. The key part with AI is that you need to be very consistent. And so essentially what we did is we identified 100,000 pages. We gave that to 50 annotators. We had an annotation manual of 100 pages to these annotators, how to do it. And we made actually a data set of 100,000 pages that is now state of the art, where we actually give you a little bit of an idea what humans can do. So basically, this table is what currently humans can actually do in performance in just annotation. So if you just take 50 humans and you try to get the layout out, this is roughly the accuracy you get. Right? And now, basically, our machine learning models are getting to that accuracy. If you now go over that, you're basically overfitting. So it gives you a very good thing. And all of the other data sets, they don't have this human benchmark. Table understanding, another beautiful one. So first of all, you want to get all of this structure out. So we did a lot of work here. Again, this algorithm that we published this year is the first end-to-end without any rules. So we just basically built a machine learning system such that it can actually work. And effectively what it does is it takes the image and it translates that to a string of tokens, essentially, and the tokens especially encode essentially the structure. And the tokens you can use, for example, HTML, and map that up. And then you can see here, like our models essentially get state-of-the-art, like if you look with other types of commercial things, which have actually a lot of human rules in there, which break it. I told you that we make things public. So here's our first part, and we'll keep pushing out. So this is on Deep Search. We have already, like you can press that big blue button, you can drag and drop your PDFs, and you can see already what we do. And so the conversion is already fully public, used by academia. There is no cap to that. The inspector is capped to 20 pages because we want to have throughput. If you use it from the client, then you can actually run as many as you want. Of course, don't put the proprietary data. I would not advise you to do that. We have also another one where you can do that. And you can actually see how it works. So I just uploaded a document that I found that looks similar to what Nestlé provided me, but it's a public one. So just so that you can actually see like how the tables are coming out. And then once we are there, once we have done the document ingestion, then there's two other things. On the one hand, you can start doing shallow search. So we have prided ourselves, it's not just doing that like a very, very accurate models that are very expensive, and so you can run it on 3 documents and then otherwise, you run out of time. So we can do around 300 pages a second on 200 nodes in the cloud. And so that means that we can ingest all of medRxiv. Actually, we have ingested medRxiv, ChemArch, all of the different archives, PubMed, the patents, and so on and so forth. And this gives us the capability to start very quickly start doing searches across the board. And we will now start adding on top of that natural language processing, so we can actually find entities, link those entities, and so on and so forth. So all of that is pre-done. And that is basically our benchmark that we plan also to actually make public as long as the licenses basically allow it to us. So all of the patents will be there. We already have the Korean, Japanese, European, US, and so on and so forth. And also there, again, here, what we do is we take all of the documents and then, for example, identify all of the images, classify the images, and a big part that we're now doing is like computer vision for molecular images. So you know that patents are, some of the patents have like an enormous list of molecules that are not reachable because they're just the image. There's no text or anything like that. We just say we patent that one. And so we're extracting all of those and making that available. And I'm hoping that like towards mid of October, we can start making that freely available so that all of you guys can search that. And then last but not least, so that is not now, so what I said before is actually the shallow search. The last part is what we call deep search. So in deep search, what we are doing is we're saying, okay, you have, for example, all of these documents, you have filtering that you can do, you can look at all of the tables. You can then apply NLP, that's what we're running at a large scale now on all of these documents. And now I can actually start extracting all of the entities and relationships such that, for example, I can get all of the statements out. So this is something, I now have my pet project. I did, theoretical physics, I did my stuff in superconductivity, so I'm rerunning that to see if we can actually find new materials that are superconducting. But it can actually be used across the board by applying this NLP. And so the way we did it is that on the one hand, the platform allows you to upload any documents. We will have already pre-curated document collections, but if you have other document collections that you want to upload, you can do that. And it also allows that if you have developed your own NLP with your own entities and relationships, you can wrap that up into an API interface and actually deploy that straight on the thing and create your custom knowledge graphs that could be used and give you insights. So these are the two things that open it up and allow you to actually very quickly get a deep grasp. And then with the knowledge graphs, you can really go very, very deep. So you can actually say, give me now all of the properties of all of the known materials that are there. Again, something that we want to run at scale, and especially in the material science domain, make that open and public. And if somebody reaches out and says, hey, I have a great idea for another topic, then we are for sure open to do that too. Yep. Good.
All right. So I'm talking this morning on effectively leveraging local food ingredients, a case study from Ghana. And I'm actually in the Department of Food Science and Technology at KNUST. This is my beautiful university, which is about 270 kilometers from the capital city of Ghana, that is Accra. As was said previously by Prof. Taylor, food insecurity is quite high in Ghana, and we have about 3.6 million households who are food insecure out of the 8.3 million households. And this has led to inadequate food nutritional intake, protein energy malnutrition, and then micronutrient deficiencies, general nutritional malnutrition. And if you look at the figures, the first figure shows how food insecurity keeps increasing over the years. And then the second figure is also telling us the spread of food insecurity, with the upper regions of Ghana or northern regions of Ghana being more food insecure. The irony of the matter is that there are a lot of available local ingredients, but these ingredients are actually underutilized. So our focus is to find ways and means of promoting these underutilized food crops to enhance food security and then meet nutritional needs of Ghanaians. And we do this by looking at the nutritional profile or compositional analysis, and those that are of benefit, we create the awareness. And then we either process them, find a way, depending on the nature of the commodity, we find a way of processing to incorporate into already existing food products, or new products are developed from them. And if you see the products that we have on the right, these are products that students have explored from local ingredients that are either going waste due to high post-harvest losses, or they are underutilized. So I'm going to talk about three food commodities or food crops that are very important to us. They are stable, they are available, and they could contribute to nutritional security and food security. The first one is orange flesh sweet potato that Prof. Taylor talked about, which has high beta-carotene, which could be converted to vitamin A. And then it also comes with a appreciable amount of minerals and vitamins. And it is also a low-caloric food, but it is easily grown in our environment. You can just throw it at your backyard, and within 3 to 4 months, you have your sweet potato harvest. It has been reported that about 125 grams of orange flesh sweet potato per day can actually reduce or prevent the development of vitamin A deficiency in children and protect them from night blindness, which is an issue. So just this quantity could do that. Then it is something that we need to push, we need to promote, so that the ordinary Ghanaian, the poor, those who are having these micronutrient deficiencies, could have access and be better off. So we use local or traditional processing methods, not expensive, because when it is too expensive a technology, our people cannot afford. So we use simple technologies like drying, where the sweet potato is chipped and it is dried and then milled into flour. Then it is also pureed, where it is possible, grated, mashed, and then pureed. And these are substituted in different kinds of products. The key one that we are very much interested in is wheat-based products. It has become very important for us in the sense that Ghanaians' taste for wheat-based products keep increasing. Meanwhile, we don't grow wheat. So we are finding alternative ways of getting our local materials to be incorporated, either to be used as wheat-based product or to be incorporated with wheat and then produce these same products for. And it has a lot of advantages. Create jobs along the value chain, and also we can, those that have nutritional benefits can also be used to address nutritional needs. So one of our research that was done on bread showed that when you use the puree, you actually retain more beta-carotene or vitamin A in the product than when you use the flour. But it is inevitable to not use flour, because if you want all year-round availability, then it is good that you process it into flour. So we've done work on biscuits, on bread, that people really appreciated. And even the color of the orange flesh sweet potato comes with an advantage, because already people add unapproved colors to some of these products to make them more attractive. So using orange flesh sweet potato becomes an advantage. Then we also do complementary foods using millet. As we heard, millet is also very good in terms of minerals and some vitamins. So we have millet, we have soya bean, and then sweet potato that is blended together to make complementary food. And with this very one, the most preferred complementary food, the formulation was 50% orange flesh sweet potato, 15% millet, and then 35% soya bean flour. And then the product was actually compared with an existing locally made complementary food and then a commercial complementary food. And you realize that the orange flesh sweet potato based products had quite a higher amount of nutrients that were determined, with the exception of zinc that was lower for calcium as compared to the commercial product. Then, as I said, usually when you add these ingredients to already accepted foods, it is usually people or the populace are able to pick it faster. So, or in terms of acceptance, it's far better. So we've also done orange flesh sweet potato in yogurt, where it's added to milk and ferment. Then you have your colored milk, colored yogurt. Or the orange flesh sweet potato has some properties like, fruit. So the juice could just be squeezed, and then you have your sweet potato drink. And usually you could add ginger, lime, or any of the preferred spices in Ghana. And the sweet potato yogurt or drink is naturally flavored and supplemented with vitamin A and dietary fiber, presenting consumers with a healthy food choice. The second commodity I want to talk about is cassava. I think cassava is one of the commonest staple foods in Africa, and it comes with very cheap calories. The starch is highly digestible, and then it also has good dietary fiber and then resistant starch. And it feeds a number of people in Africa, 700 million people living in the tropical and subtropical areas depend on cassava. So basically, cassava is very perishable. So locally, there's a number of products that have been produced from cassava. But there's this new cassava, high-quality cassava flour that has been produced that could be used as a substitute in wheat-based products. We did studies. So basically, you dry them, you chip the roots, the fresh roots, and then they are dried and packaged as high-quality cassava flour. And this has to be done within 24 hours so that there will be no fermentation. And we did a recipe with wheat flour, as I said, because of the issue we have with the consumption of bread or wheat-based products in Ghana. And the main aim was to promote utilization of cassava flour in wheat-based products. So up to about 20% substitution was done, and this was acceptable. We had substitution levels up to 20% high-quality cassava flour for sugar bread, and then 10% high-quality cassava flour for tea bread were established to be culturally acceptable. In Ghana, we have two major bread types: the sugar bread that has more sugar, and then the tea bread that has less sugar but a little bit more salt. So for the tea bread, 10% substitution was good for it. It was acceptable. People could not differentiate it between that and then 100% wheat flour. And in the same way, sugar bread, we had 20% substitution that could be accepted without knowing the difference, whether cassava flour has been added or not. The issue is that we had to do glycemic index and glycemic load determination, because the ordinary Ghanaian, even though cassava is a very staple food, the ordinary Ghanaian looks down on cassava. And if they find cassava in bread, they would not take it. Thank you. They will not take it. So we did glycemic index and glycemic load just to have some health beneficial component of what cassava brings along, so that people, that could be used to promote the intake or consumption of cassava wheat composite bread. And then we find out that 10%, 100% wheat bread had medium glycemic index, whilst 10% substitution and 20% substitution actually lowered it. For the sugar bread, 100% wheat bread was high, but then 10-20% substitution lowered the glycemic index, which is good for those who have sugar-related issues, health issues. And then we also did instant cassava-based complementary food. Because of time, I wouldn't go much into it, which was at least the nutritional composition was better as compared to just using cassava. Then we also improved an existing biscuit, which is mainly made from cassava and then coconut. We improved it with cowpea, and then orange flesh sweet potato. So the main thing is to actually add some of these nutrients that have specific good nutrients to the existing food products that we have, so that the nutritional composition will be enhanced. Millets, we looked at millets with Nestlé, and we did some preliminary tests using soaking and phytic treatment, and then we realized that using these reduces the phytic acid levels, as was said previously, because phytic acid content of millet is quite high. And the purpose was to develop a beverage from millets and orange flesh sweet potato. This beverage is existing already, people like it, but then we wanted to add orange flesh sweet potato to improve the vitamin A content of it. At the end of the day, we had 30% orange flesh sweet potato substituted beverage having beta-carotene content of 40 retinol activity equivalent as compared to the control, which was 5.6. So in conclusion, the potential to use local and available food ingredients to enrich existing food products or develop acceptable nutritious food products is high and must be encouraged through research. There is the need for industrial support in fine-tuning and commercializing these potential food products. Thank you very much.